Hello, algebra students, and welcome to your lesson on simplifying square roots. I'm going to be presenting it using the copy of the blank notes, so if you do have a printer, feel free to print this off and follow along. If not, you can always take notes on your own paper. But I thank you in advance for your patience while I try different ways to present the lesson, just getting ready for next week when we start our virtual classes. Just like always, though, we're going to start off with these two review questions here. If you want to go ahead, pause the video and try numbers 1 and 2. All right, for this first equation here, I would be using y equals mx plus b to help me figure out what that equation is. There we go. When you are using this formula here, y and x always stay in your equation. M is going to be your slope. In this case, with these 2 points, I can see that we're going down 3 over 1, which means the slope is negative 3. We've got y equals negative 3x. And then b is always your y-intercept. Here, this line crosses our y-axis at the point 6. So my y-intercept is a positive 6. And that right there would be our equation. I'm going to make this a little bit smaller. For the second one here, we've got what is the slope of the line that passes through these 2 points. I'm using that formula y2 minus y1, all divided by x2 minus x1. When we use that formula, y2 is 4, y1 is 10, so we get 4 minus 10 all over x2 minus x1. x2 is negative 2 minus x1, which is 1. That's going to end up giving us 4 minus 10, which is negative 6, all over negative 2 minus 1, which is negative 3. Let me stick that negative sign up there. And then negative 6 divided by negative 3 gives us a positive 2. So to answer the question, what's the slope? The slope is 2. With that, we will go ahead and get started. Down here, the objective for this lesson is how you simplify square roots. There's also going to be a couple questions to help us prepare for our lesson on Monday, which is on something called the quadratic formula. So I will kind of put in here, part of this lesson is focusing on some quadratic formula prep. The questions for the preparation for quadratic formula aren't questions you would ever have on like a test or a final exam. But when we go to use quadratic formula next week, there's a lot going on. And so we're just going to be doing some preparation for it to help make Monday's lesson go smoothly. With that, though, we are going to start on this first part, which is on simplifying square roots. In order to simplify square roots, there's going to be some words that you hear me say. That first word, it seems to be the word of the week, is factor. At this point, we're pretty good at knowing factor. Factors of numbers are just 2 numbers that multiply to get, I'm going to call it a goal number. So for example, lots of times we're talking about like factors of a specific number. I could say the factors of 10 are 1 and 10 and 2 and 5. So I'll label that as my example. It's just pairs of numbers that multiply to get that goal number. In this case, it's a 10. So in order to simplify square roots, we're going to be looking at factors. Now, as we are looking at those factors, we're going to be looking for prime numbers. Prime numbers are numbers that are only divisible by 1 and itself. Now, I'll start with an example, and then I'll have you think of a couple prime numbers. An example of a prime number could be the number 5. 5 is prime because the only numbers you can divide 5 by are 1 and itself, and 5. Can you think of some other prime numbers? Usually in class, the first couple I hear 3, I hear, not 67, I hear 7. Sometimes students will throw out 9. They're like, it's just a bunch of odd numbers. 9. 9 is not prime because you can divide 9 by 3, but 11 is prime. 13 is prime, 15 isn't, 17 is prime. At some point, students usually ask, well, do prime numbers have to be odd? And the majority of prime numbers are odd, but there is one number that is not odd that is prime. Do you know what that one number is? The only even prime number is the number 2. 2 is prime because the only numbers you can divide 2 by are 1 and itself. So 1 and 2. Obviously, this list keeps going on and on. There are some prime numbers that are quite large. I wrote 67 earlier. 67 is actually a prime number, but you could have prime numbers even larger than that. Prime numbers go on and on and on forever. But in today's lesson, we're really not going to see any prime numbers that are too large. The last thing you're going to be hearing me saying today is this idea of making a factor tree. Factor trees are a method you can use to help you simplify square roots. And what a factor tree is, it looks like a tree, but it's where you break a number or the process where a number is broken into prime numbers. And that definition is going to make a little more sense when we start looking at some of our examples. We are going to start off by simplifying the square root of 72. Now, when we talk about square roots, up until this point, at least in my class, you have not had any square roots you couldn't find the square root of. For example, you can find the square root of 25. Square root of 25 is 5. You can find the square root of 49. Square root of 49 is 7. I've only given you numbers that are perfect squares, meaning numbers that you can find a square root of. Now, 72 does not have a square root. There is no number that when multiplied by itself gives you 72. No whole number. You could type square root of 72 into your calculator and get a decimal, but there's no perfect whole number like the square root of 25, square root of 49, etc. What you can do, though, with square roots that don't have that perfect whole number answer is you can simplify them. Kind of like when we simplify fractions. There's a process to simplify square roots as well. There's actually 2 methods you can simplify square roots with. I'm going to show this method first, since after teaching this lesson for 7 years now, this is the method that more students really connect with, that they like. And then after this one, I will show you a different way you can simplify square roots. But we are going to use a method that involves making a factor tree. How a factor tree works is you are going to start off with the number inside the square root, and you are going to come up with any 2 pairs of numbers that can multiply to give you 72. And these, you kind of draw branches coming out of it. There are a lot of different pairs of numbers you could start off with that give you 72. You want to just pick a pair that's not 1 and 72. You want to pick 2 numbers that multiply to give you 72 besides 1 and 72. Like I said, lots of different pairs you could be thinking of at home. The one I hear a lot in class is 8 and 9. 8 times 9 gives you 72. Now, the way the factor tree works is you are going to keep going. You are going to keep making more and more of these branches with factors of these numbers until you are only left with prime numbers, which is why we said a factor tree is the process where this number is broken into primes. So if I wanted to keep going, I'm looking at 8. 8 is not prime. I can think of another pair of numbers that multiply to give me 8. And that pair of numbers I'm thinking of, do you know what I'm thinking of? Is going to be 2 and 4. If I look over here at the 9, 9 also isn't prime. I could come up with another pair of numbers that multiply to give me 9. That pair of numbers is 3 and 3. 9 times 1 also gives you 9, but remember we're looking for pairs of numbers that aren't 1 in itself. Now if I keep going, remember our goal is to break it into prime numbers. If I'm looking at 2, 2 is prime. Means I'm not going to keep going with 2. 4 is not prime. So I'm going to continue my pairs of numbers. 4, we could split into 2 times 2, because that gives me 4. And then if I come over here, 3 is prime, 3 is prime. So at this point, I have got a bunch of prime numbers. I'm going to go ahead and circle them all. we've got 2, 2, 2, 3, and 3. Now, the other part of this idea of breaking a number into primes, what it means is I should be able to multiply all of these back together. And what do you think I'm going to see? Well, to find out, let's do it. If I do it, it doesn't matter the order. But 3 times 3 gives us 9. 9 times 2, 18. 18 times 2, 36. 36 times 2 gives you 72. So all we're doing is changing 72 into like a multiplication problem that's using a bunch of prime numbers. Now, once you have all those prime numbers, you are looking for pairs of numbers. And by pair, I mean 2. We're looking for 2 of the same number. I'm going to mix up my color again. I'm taking advantage of having all these different colors here. So if I look through all these prime numbers, do you see a pair of numbers? Why, yes, I see a pair of 3s. So I've got one pair of 3s. Do you see any other primes? Yeah. Or sorry, not primes. They're all primes. Do you see any other pairs of numbers? And the answer is yeah, we got a pair of 2s. Sometimes students think they have to be next to each other. They don't. Just looking at all of your primes here, do you see any pairs? So I see I got a pair of 3s, one pair of 2s, and then I've got a 2 left over. When we go to simplify the square root, what we are going to do is if there are a pair, the pairs are going to go outside the square root, and then any numbers go away. Any numbers by themselves will go inside your square root. So notice I have one pair of 3s, so I'm going to put 1 3 outside my square root. It's 1 3 for one pair, so not 2 3s, just 1. And then I have one pair of 2s, so I'm going to put 1 2 outside. And then I've got 1 2 by itself, so I'm going to have that 1 2 inside. And then if you have more than one number next to each other, you connect them with a multiplication sign. So I've got 2 times 3 times the square root of 2. The last part to this is simplifying. 2 times 3 gives us 6. And then we just need to copy that square root of 2. This right here is our final answer. What we are saying is that the square root of 72 equals 6 times, there's like a little invisible multiplication sign there. Square root of 72 equals 6 times the square root of 2. If you were to grab a calculator, type in the square root of 72. We said earlier it's going to give you a decimal. Let me go ahead and do that for you. And you can, if you're at home, fact check me and make sure it's right. We get the square root of 72 is 8.485, and then the decimal keeps going. If you were to type in the square root of 2, the square root of 2 equals 1.414, and multiply that by 6, you're going to end up getting the same decimal. You're getting 8.485. So in decimal form, these two things equal each other. We're just simplifying the square root, meaning you're making those numbers smaller. I should have said earlier, but I'll say it now. The reason we are learning this skill is because it's going to help us. Remember, I said at the beginning of this lesson, next week we're looking at something called the quadratic formula. This right here is going to help us with that quadratic formula and help us on our quest to learn everything about quadratics in this unit. So there's a reason behind this. The steps are right here. I'm going to jump down. I'll leave them up there and jump down to number 2. We've got the square root of 120. If you're feeling like, yeah, I like factor trees, this looks good, I encourage you to pause the video now and try it. If you are like, what the heck is going on? Don't worry, because I'm here to do another example for you. So we've got the square root of 120. We're going to start off by doing what? We're going to start off with that factor tree. So I'm going to take my 120 and pick 2 factors that give me 120. Now I encourage you, if you didn't earlier, pause and just make your own factor tree. Don't worry about like all of this. Just pause after you've gotten the factor tree. Now, the reason I asked you to try making a factor tree first is because a lot of us are going to start off our factor tree differently. If you've got 120, you could use 12 and 10. You could use 6 and 20. You could use 60 and 2, 30 and 4. There's so many different possibilities for how you start your factor tree. I think I personally am going to use 60 and 2. And depending on how you start your factor tree, it could look different. So unless you use 60 and 2 at home, your factor tree is going to look different than mine. I'm starting with 60 and 2. 2 is prime. That's nice. So I just need to keep going with 60. 60, look, I'll use 2 again. 2 and 30. If I want to keep going with my 2s, I could say 2 and 15. 2 is still prime, but 15 is not. 15, we could say 3 times 5, and then both of those are prime. So when I look at what I'm left with as far as prime numbers go, I have a 2, a 3, a 5, a 2, and a 2. Those are all of my prime numbers. Now, if you started this differently, your tree might look different, the shape of it might look different, but you should have all of these same prime numbers. You should have 1, 2, 3 2s, a 3, and a 5. And again, if we were to multiply all these back up, it would give us 120. 2 times 3 is 6, 6 times 5, 30, 30 times 2, 60, 60 times 2, 120. So we've got all our prime numbers here. What am I doing with my factor tree? What was that next part? Here's your clue. Well, that next part is we're looking for pairs of numbers. So I've got all of these primes here. Do you see any pairs? Well, yes, I see a pair of 2s. I've got 1, 2 here and another 2 here. So I've got one pair of 2s, and that's it. None of these prime numbers that are left are the same. Once you've got your pairs, when we go to simplify our square root, what are we doing with those pairs? Well, if there's a pair, it goes outside the square root. So one pair of 2s means 1, 2 outside. And then all of these numbers that are by themselves all go inside. So we've got a 2, we've got a 3, and we've got a 5. And notice I've got those multiplication signs between them. To finish off, I'm just going to simplify. So we've got 2, and then square root of 2 times 3, which is 6. 6 times 5, which is 30. So we get, 2 square root of 30. That means is the square root of 120 is the same thing as 2 times the square root of 30. And that is everything we can do to simplify. I've got one last example. If you're feeling excited, you can go ahead and try it if you want. This one is a little different than the other one. This one here, we're still simplifying a square root, but this one here is starting off with a number in front of your square root. That's okay. It just means when I go to do this step here, I'm going to still be using all these primes, but if I had a number in front, so let's say there was a 7 right here, it just means when I go to place all my numbers, I'm starting off with one already outside. The rest of it's going to be the same. So we're going to start by making a factor tree for the square root of 18. If I think of pairs of numbers that multiply to give me 18, I could use 3 times 6. And then 6 is not prime. I could say 6 is the same thing as 2 times 3. And that's everything. So I've got my prime numbers are 3 times 2 times 3. I'm looking for pairs. There's a pair of 3s. My pair of 3s goes outside the square root. That 2 that's by itself, ooh, goodness, goes inside the square root. And then don't forget, we have that 1 7 that was already outside. So when I'm placing all my numbers, I need a 7 outside. My final answer is going to be 7 times 3, which is 21. And then we've got the square root of 2. And that right there is our final simplified 7 square root of 18 is equal to 21 times the square root of 2. Hopefully you're feeling all right to try these two here. Have you go ahead, try number 1 and try number 2. All right. This first one here, you should have gotten 2 times the square root of 6. And then this other one here, you would have gotten 15 times the square root of, there you go, 10. All right. Now, if you are wondering how I did this so fast without any factor tree, it has to do with the second method I was talking about. Remember, when we were all the way back up here, I said these steps right here are the steps that a lot of students in the past have ended up using to help them simplify square roots, but there is another method. And so to show you that other method, I'm actually going to erase like this. Well, I'm going to erase all of this and then show you the second way. There it goes. The second way has to do with square roots of numbers that do have perfect square roots, perfect whole number answers. When you think of numbers that do have square roots, I'm going to write some off to the side here. Go away. For example, the square root of 4 that has a perfect square root. The square root of 9 has a perfect square root. You could keep continuing to make this list if you want to pause the video and do it yourself. I'm going to just write a couple more. So notice I've got 2, 3, 4. 5 would be square root of 25. 6 would be square root of 36. This is where knowing your multiplication well really comes in handy. And that part about knowing your multiplication is why this method works really well if you just know your facts, like right off the top of your head, don't have to think about it. But if you're someone who it takes a little longer to come up with those multiplication facts, this might really be the way you connect with. The second method here uses all these perfect square numbers, and obviously this list could keep going. What the second method does is if you are trying to figure out the square root of 72, to use this second method, your goal is to figure out the largest perfect square number you could use to write a multiplication problem and get 72. For example, I know that 36 times 2 gives me 72. So what this method says is let's rewrite that. We're going to write the square root of 72 is the same thing as the square root of 36. I don't want to use that multiplication. There we go, 36 times 2. Now, we said earlier, there's a lot of different ways you could multiply to get 72. I think I earlier used 8 times 9. You could use 12 times 6. 36 times 2 is one of them. But I'm specifically choosing this one because one of those numbers, 36, is a perfect square number, and it's also the largest one I could use. So notice I'm not choosing, my goodness, I'm not choosing 8 times 9 because 9 isn't the largest number on this list, 36 is. Once I've done that, we can go ahead and say, well, the square root of 36 times 2, that is the same thing as the square root of 36 times the square root of 2. So all I've done is I've split up those two numbers and put them both in their own square roots. Now, why is that helpful? Well, the square root of 36, I can do that. That's the reason I chose this pair, right? The square root of 36 is 6. Square root of 2, I can't do that. So it'll just stay in its own square root. And I went ahead and erased mine, but since you've been taking notes down, you can look at your notes and see this is the same answer we got earlier. This way looks a lot shorter, and I would argue it is a lot shorter if you know that multiplication, right? If coming up with 72 equals 36 times 2 is difficult for you, this probably isn't going to be your method. I'll do one other example of this. So this one here, the square root of 24, I wasn't doing a factor tree that quickly in my head. What I was doing was I was saying, well, the square root of 24. Do you know what pair of numbers I used? I'm specifically using the pair 4 times 6. Not using 12 times 2 or 3 times 8. I'm using 4 times 6 because there is a square root of 4. So if I say it's the same thing as 4 times 6, then I could go ahead and say, well, that's the same thing as the square root of 4 times the square root of 6. And then from that, I could say, well, the square root of 4 is 2. Square root of 6, nope, can't do it. So it stays square root of 6. And then look, same answer. So I'm going to give you one last problem to try. You can choose your method. So if I've been doing this and you're like, oh my God, like, what is this crazy magic you're doing? Then maybe stick to these steps. If you want to try this new method, though, this problem here is for you. I'm going to have you simplify the square root of 300. And go. Alrighty, so if you are using this new method to do that, you would want to split the square root of 300 into 100 times 3. That is helpful because the square root of 100 is 10. Square root of 3, we can't do, so we just leave it square root of 3. If you were doing a factor tree, it would be a very big factor tree. But you would end up having a pair of 2s and a pair of 5s that you could pull out to make that 10. And then there would be 1 3 by itself that goes inside the square root. This right here is the end of part 1, which is on simplifying square roots. Remember, there's just a couple questions at the end of this lesson to help us prepare for Monday's lesson. So we'll do some of that quadratic formula prep now. The first part here is just a reminder of the quadratic equation form. You all know this at this point. We've been saying quadratic equations are any equation that are in the form ax squared plus bx plus c. And then when it's an equation, we said it must equal 0. And there we go, make it easier to see. So one of the things we are going to have to do on Monday to use something called the quadratic formula is look at a quadratic equation and identify A, B, and C. Now, when it's in this form, it's super easy because A is just going to be the number in front of x squared, B is going to be the number in front of x, and then C is going to be that number at the end. So for example, in this equation here, what is A, B, and C? Well, A is going to be the number 2. Sometimes people want to say 2x squared. A is just the number in front of x squared. So we're just going to say 2. B is the number -3. Make sure you don't forget that negative sign. And then C is that number -5. Where it can be a little tricky is when you look at a quadratic equation and it's not already in this form. Can you guess what we are going to do? Well, we're going to change it to look like this form. So for this equation right here, I can change this equation into this form by making sure the equation equals 0. Now, right now it equals 3b. If I want it to equal 0, what do I have to do? Well, I've got to get rid of the 3b, and I'm going to do that by subtracting 3b. So if I've got 4b squared plus 8 equals 3b, if I were to come in and subtract 3b on both sides of those equations, there's like 3b's all over the place. If I subtract 3b's on both sides of 3b on both sides of the equations, what would it look like? Well, over here it would equal 0. On this left side, I cannot subtract 3b from anything. Some people want to subtract it from 4b squared, but notice b squared and b are not like terms. You can't subtract it unless they both have the same exponent. So I'm just going to end up having all 3 of these terms on that left side. I want to keep them in this order. That's the most helpful order. So I'm going to have b squared first, and then the b, and then the 8. So my final quadratic form would be 4b squared minus 3b plus 8, and then it equals 0. Once you've done that, you can probably take over at this point. What are A, B, and C going to be? Well, A is going to be the number 4, B is going to be the number -3, and then C is going to be the number 8. Go ahead, pause the video now, and try 3 and 4. All right, here for 3, there's no number in front of x squared. When you don't see a number, it means that number is 1. B, be careful. This one looks like it's in quadratic form, but it's a little out of order. We've got x squared. Next, the x, that's where your b is. B would be the number -5. And then c is always that number by itself, that constant, which here is that positive 6. Whoops, but I don't need the positive sign. I can just write 6. This one here, you would have to solve that equation by subtracting 25 on both sides. That's going to look like x squared minus 25 equals 0 once you've done it all. After you've got that, it helps you figure out A, B, and C. A, once again, there's no number in front of that x squared, so we've got another 1 for A. That minus 25, is that your B or your C? Well, B is the number with x, and this one doesn't have an x. So that must be the C. What do you think B is? Well, if B is missing, there is 0 B's, or sorry, 0 X's in the equation. That means B is 0, because literally there are 0 X's. This is the first part of our quadratic formula prep. The second part here, part of the quadratic formula is going to have us evaluate something that looks like this. This is just part of the formula, so I want to practice with this part first before we throw everything at you on Monday. But this goes back to a pre-algebra skill, which is just if I give you different numbers, can you evaluate an expression? So in order to figure this out, all we got to do is substitute in these numbers and then figure out what it equals. So for this one here, I've got the square root of b squared. Well, I can start off with my square root. B squared, instead of writing b squared, b is 10, so I'm going to write 10 squared minus 4ac. So minus 4, a is the number 1, and since it's written 4ac, there's nothing in between them. That means multiplication, so it means minus 4 times a times c. So I'm going to write minus 4 times a, which is 1, times c. C is 9. And then all that's left is doing some fun math. So we've got the square root of 10 squared. Well, 10 squared equals 10 times 10, which is 100. Then minus 4 times 1 is 4. And then times 9 is 36. So we get the square root of 100 minus 36. You can break this up into parts if you want, that multiplication. So you could always go ahead and say, well, my first step is the negative 4 times 1, which is negative 4, and then multiply the negative 4 times 9 and get your negative 36 that way. It's up to you if you want to do it all at once like I did there, or break it up into little steps. Either way, you're going to get 100 minus 36. 100 minus 36 is 64. But we could keep going because the square root of 64 is 8. Notice, just a reminder, when you take square roots of numbers, we don't need a square root in our answer. The square root of 64 is 8, not the square root of 8, just 8. I mentioned that because sometimes I will see some square roots still in the answer. And that is as much math as we can do. So I did this first one. I don't think we'll do all of them. Let's just choose, I'm going to have you do this one here for me. Oops, but you probably need that. There you go. All right, so this one here, we've got the square root of b squared. Well, b is negative 2, so I'm going to write negative 2 squared. Using those parentheses just to show that that number is negative. It's negative 2 we're squaring, not just 2. So we've got negative 2 squared minus 4 times a times c. I certainly gave you a fun one with all these negatives. the next step there would be negative 2 squared. Now, what did you say negative 2 squared was? Negative 2 squared is negative 2 times negative 2, which is positive 4. So we get positive 4, and then we're going to multiply all of this together. I might break it into parts. So I'm going to start off by saying negative 4 times 2 is negative 8. And then I'm just going to copy down that times negative 12. And then once we've got that, we could say 4 and then negative 8 times negative 12. Well, a negative times a negative gives me a positive, and 8 times 12 gives us a positive 96. So we get the square root of 4 plus 96 gives us 100, and the square root of 100 equals 10. Now for both of these, I got perfect, nice perfect square numbers inside our square root signs. Notice 64 had a square root, 100 had a square root. Do you think that's always going to happen? No, of course not. That is why we learned all of this handy dandy stuff earlier, is because if it doesn't happen and you get something like the square root of 300 instead of 100, we also know how to simplify that now. There's one last part, and that is what to do with this weird looking sign here. You read that sign as plus or minus. And what a plus or minus sign means is exactly what it says. You think of it in two ways. You think of it as a plus sign, or you think of it as a minus sign. So if I were to ask you to simplify something, why is it so small? It says 3 plus or minus 5, all divided by 2. In order to figure out what this equals, you're going to think of it as two different problems. You're going to think of it with a plus sign, so thinking 3 plus 5, all divided by 2. And you're going to think of it with a minus sign, so think 3 minus 5, all divided by 2. So when we get to these plus or minus signs and it comes to simplifying them, you're going to break it into two different problems. After that, that 3 plus 5 gives you 8, so you get 8 over 2. You can go ahead and finish saying what that equals. 8 divided by 2 gives you 4. For this other one here, we got 3 minus 5. 3 minus 5 is negative 2. All divided by 2 gives you negative 1. Now, in this one here, we again got nice numbers we could divide. Do you think that's always the case? No, of course not. So you could have something like 9 divided by 2, 17 over 2, 1/2. They can be fractions. They can be decimals. Don't be fooled by this question thinking it's always going to divide out nicely. So the last thing for this video, I'm going to have you go ahead and evaluate this expression here. Figure out what it equals. Alrighty, how'd you do? We're going to, just like before, split it into two separate problems. So I'm going to say 14 plus 29 divided by 5. And I'm going to say 14 minus 29, all divided by 5. For the addition one, 14 plus 29 gives you 43 over 5. That cannot be simplified, although you could write it as a decimal if you wanted. For the subtraction one, 14 minus 29 gives you negative 15 over 5. That can be simplified. 15 divided by 5 is 3, so that ends up giving you a negative 3. After these three parts, I promise this is going to make Monday's lesson go so much easier for you. So thanks for sticking around for the preparation stuff. That is everything I've got for this lesson. Thank you so much for watching. See y'all later.